A flat expanse of glacial till stretches toward the horizon, broken only by straight fence lines, gravel roads that jog sharply to the side, and pump jacks moving against the gray sky. There are no sudden cliffs or visible fractures in the soil. To anyone driving along these rural ranges, the land appears predictable, an expanse of clay, gravel, and prairie grass resting on solid ground. Then the survey data arrives. Beneath this quiet surface, extending across thousands of square kilometers, lies a geological structure of immense volume that went unrecognized by early settlers and cartographers for more than a century. It was not until systematic deep drilling and modern seismic profiling mapped the subterranean horizons that geologists realized the surface plane is merely a thin mantle resting on a complex, unstable basement. What does it mean when the foundation of an entire region is shaped by ancient, invisible forces operating thousands of meters beneath everyday pastures? We examined 20 distinct geographic anomalies across the census divisions of the Canadian prairies and western interior, from subterranean salt structures and impact craters to drowned glacial riverways and lost industrial settlements. Before modern geophysics, land surveyors in the 19th century assumed the interior plains were a simple wedge of sedimentary rock dipping gently eastward. The surface topography was flat, river valleys were young, and early shallow wells yielded predictable layers of clay and gravel. But the first crack in this assumption appeared in the logs of deep exploration wells drilled across the Saskatchewan Plains and Alberta syncline. Our journey through these hidden phenomena counts down across the region. Far from being a featureless slab of earth, the prairie interior sits atop dynamic subterranean mechanics. Item 20. The subterranean halite giant of the Prairie Basin. Directly beneath the agricultural surface of central Saskatchewan lies a salt deposit of astounding proportions, the Prairie Evaporite Formation. Reaching depths of over 1,500 meters, this solid sheet of halite and potash covers more than 200,000 square kilometers. Formed over 380 million years ago during the Middle Devonian period, when an ancient inland sea evaporated, the weight of overlying rock compressed the salts into a dense layer up to 200 meters thick. Where groundwater circulating along deep fault lines contacted the salt, massive dissolution caverns formed over geological time. At locations like the Crutwell collapse feature, the roof over these voids gave way, swallowing surface sediments and altering localized drainage patterns. Today, solution mining operations tap into this deep halite sheet, extracting millions of tons of rock salt and potash annually from caverns situated hundreds of meters below rural wheat fields. Item 19. The drowned valley of the preglacial river systems. Long before continental ice sheets carved the modern course of the South Saskatchewan and Missouri rivers, an ancient river network drained the interior of the continent. Known to geologists as the Tyner Valley and associated preglacial channels, these deep bedrock valleys were carved tens of millions of years ago into soft Cretaceous shale. When the Laurentide ice sheet advanced across the region during the Pleistocene epoch, it filled these wide, steep-walled canyons with hundreds of meters of glacial drift, gravel, and crushed till, erasing them from surface topography. Today, no trace of these ancient valleys appears on standard topographic maps. However, hydrological monitoring by the Geological Survey of Canada confirms that these buried valleys persist as massive subterranean aquifers. Rainwater and snowmelt percolate through the porous gravel fill, creating hidden underground rivers that feed municipal wells and maintain regional groundwater tables across hundreds of kilometers of prairie. Item 18. The impact structure of the deep basement. Topography near the town of Viewfield in southeastern Saskatchewan gives no hint of the cosmic event buried deep beneath its topsoil. Beneath 200 meters of flat sedimentary layers lies an impact crater roughly 2.4 kilometers in diameter. Created approximately 190 million years ago during the Jurassic period when a meteorite struck the Earth, the impact shattered the underlying Mississippian limestone, creating a rim of fractured breccia and a central structural uplift. Over millions of years, subsequent sediments buried the crater, completely leveling the surface terrain. Because shattered rock within the rim created porous reservoirs sealed by overlying shale, the invisible crater became a primary structural trap for oil migration. The discovery of this subterranean impact zone in the mid-20th century proved that ancient extraterrestrial events actively shaped the modern distribution of deep natural resources across the interior plains. Item 17. The landslide megastructure of the Frank Slide. On April 29, 1903, at 4:10 in the morning, 82 million tons of limestone detached from the summit of Turtle Mountain in southwestern Alberta. Within 100 seconds, a wedge of rock 150 meters thick, 800 meters wide, and 1,000 meters long slid down the east face, accelerating across the valley floor at speeds exceeding 100 kilometers per hour. The collapse buried the southern edge of the coal mining town of Frank, crossing the Crow's Nest River Valley and climbing over 30 meters up the opposite slope. Geologists from the Geological Survey of Canada determined that the failure was driven by structural weaknesses within Paleozoic limestone, where ancient thrust faulting created steep, unstable joints. Millennia of freeze-thaw cycles combined with underground coal mining at the base of the mountain triggered the movement. Today, a debris field of giant boulders spanning 3 square kilometers remains frozen in place across Crow's Nest Pass. Item 16. The subterranean rifting system of the Midcontinent. Deep beneath the sedimentary soils of southern Manitoba lies an ancient geological boundary, the Trans-Hudson origin and its associated rift zones. Formed roughly 1.8 billion years ago during the Proterozoic Eon, this collision zone marks where ancient continental fragments smashed together to build the core of North America. Deep seismic reflection profiles conducted by lithoprobe reveal that the continental crust beneath this region is deeply fractured, featuring fault-bounded drop-down blocks known as grabens. As deep crustal movement occurred over geological time, fluid minerals migrated along these faults, concentrating rich deposits of copper, zinc, gold, and nickel in localized volcanic belts such as the Flin Flon Greenstone Belt. Though buried beneath hundreds of meters of flat Paleozoic limestone and Quaternary till, these ancient Precambrian rifts continue to exert structural control on regional hydrology and subsurface fluid movement across the province. Item 15. The crater lake of Pingualuit. In the northern tundra of Nunavut, Quebec, sits an almost perfectly circular body of water, the Pingualuit crater. Measuring 3.44 kilometers in diameter and reaching depths of 267 meters, this isolated basin holds some of the purest freshwater on Earth. Formed approximately 1.4 million years ago when a meteorite struck the Canadian Shield, the force of the impact excavated a deep bowl into ancient granite bedrock, raising a sharp rim that sits 160 meters above the surrounding plateau. Because the crater has no inlets or surface outlets, its water accumulates entirely from rain and snowmelt, producing an exceptionally transparent liquid column. Sediment cores recovered from the lake floor by scientific expeditions provide an uninterrupted record of regional climate variations spanning multiple glacial cycles, preserving environmental signatures that were scoured away on the surrounding landscape by advancing ice sheets. Item 14. The volcanic ash horizons of the Cypress Hills. Rising over 600 meters above surrounding prairie plains along the Alberta and Saskatchewan border, the Cypress Hills represent a unique topographic anomaly. During the Pleistocene epoch, when continental ice sheets covered almost all of western Canada, the highest summits of the Cypress Hills remained unglaciated nunataks, projecting above surrounding ice. Exposed along steep eroded bluffs are distinct light-colored beds known as the volcanic ash horizons of the Cypress Hills Formation. Approximately 30 million years ago, during the Oligocene epoch, violent explosive volcanic eruptions in the Cascade Range and western interior launched massive clouds of fine ash into the upper atmosphere. Prevailing westerly winds carried this volcanic glass hundreds of kilometers eastward, depositing thick layers across ancient river floodplains. Over millions of years, these ash beds mineralized into bentonite and silica-rich siltstone, creating hard caprock layers that protected the plateau from regional glacial erosion. Item 13. The buried bitumen basin of the Athabasca. Spanning more than 140,000 square kilometers across northeastern Alberta, lies one of the largest petroleum deposits on the planet, the Athabasca oil sands. Embedded within the early Cretaceous McMurray Formation, these dense sands contain hundreds of billions of barrels of crude bitumen trapped within porous deltaic sandstone. Approximately 110 million years ago, vast ancestral river networks emptied into the western interior seaway, depositing thick beds of clean quartz sand. Over millions of years, liquid crude oil generated in deep Western Canada sedimentary basin source rocks migrated hundreds of kilometers northeastward along porous carrier beds. As oil approached shallow margins of the basin, underground bacteria consumed lighter hydrocarbon fractions, leaving behind a thick bitumen coating the sand grains. Recorded in indigenous oral histories and documented by fur trader Peter Pond in 1788, these vast bitumen sands reveal how ancient river deltas created a massive fossil fuel vault beneath northern boreal forests. What happens when subsurface water driving these massive geological formations begins to move in unexpected directions? Item 12. The subterranean iron basin of the Sudbury impact. In 1883, during construction of the Canadian Pacific Railway through northern Ontario, blasting crews cut through a ridge near Sudbury, exposing dense copper and nickel ore. What early prospectors assumed was a standard volcanic intrusion was actually something far more catastrophic. It was not until the mid-20th century that geologists using petrographic analysis identified microscopic shatter cones and planar deformation features in quartz crystals, shock signatures produced only by hypervelocity impacts. In 1964, scientist Robert S. Dietz published findings confirming that the Sudbury Basin, spanning 60 kilometers long and 30 kilometers wide, was created 0.85 billion years ago by a massive bolide strike. The impact melted the Earth's crust, creating a subterranean magma sheet that concentrated massive deposits of nickel, copper, and platinum group elements around the basin rim. Modern airborne electromagnetic surveys map these deep conductive bodies, turning a billion-year-old impact structure into one of Canada's most productive mining districts. Item 11. The indicator minerals of the Slave Craton. For over a century, traditional geological maps of the Northwest Territories classified the vast tundra of the Slave Craton as barren shield rock. Because diamonds originate hundreds of kilometers inside the Earth's mantle under extreme pressure, conventional surface prospecting yielded no trace of them across subarctic terrain. In 1991, geologists Charles Fipke and Stuart Blusen changed the map of northern Canada by applying glacial dispersion analysis. Instead of searching directly for diamonds, they sampled till deposits for heavy indicator minerals, specifically chrome pyrope garnets, picroilmenites, and chrome diopsides. By mapping microchemical compositions of these minerals and tracing their glacial dispersal train hundreds of kilometers backwards against the direction of ancient ice movement, they located the source at Lac de Gras. Subsurface diamond core drilling confirmed the presence of rich diamondiferous kimberlite pipes buried beneath shallow lake waters, proving that ancient mantle minerals had been swept across tundra by glacial transport. Item 10. The deep gas sea of the Montney Formation. Deep beneath the foothills of northeastern British Columbia and northwestern Alberta lies the Montney Formation, an organic rich siltstone layer spanning thousands of square kilometers. Deposited during the early Triassic epoch in a quiet marine basin, the formation contains massive volumes of trapped natural gas and natural gas liquids. For decades, traditional exploration wells bypassed the Montney because its microscopic pore throats, measuring less than 1 micrometer across, prevented gas from flowing naturally through dense rock matrix. It was only with the advent of horizontal core logging and multi-stage hydraulic fracturing in the early 2000s that the true scale of the reservoir was unlocked. Microseismic monitoring arrays, which track tiny subterranean fracture events in real time, revealed that the Montney Formation acts as a continuous hydrocarbon sea trapped more than 2,000 meters underground, fundamentally altering energy estimates across Western Canada. Item 9. The subterranean channels of the Dominion Land Survey. When surveyors laid out the Dominion Land Survey across Western Canada starting in 1871, they used Gunter's chains and solar compasses to divide millions of hectares into a strict grid of square sections. However, because the Earth is spherical, laying parallel north-south lines on a curved surface causes grid lines to converge as they move north. To keep township boundaries uniform, cartographers introduced correction lines every 24 miles, roughly 38.6 kilometers. At these lines, east-west range lines jog abruptly sideways, creating visible offset corners along modern rural roads. Aerial photograph interpretation and high-resolution satellite imagery map these systematic survey adjustments across thousands of kilometers of prairie terrain. What appears on the ground as an abrupt road offset is actually a direct geometric correction required to map a flat grid onto the curved surface of the Earth. Item 8. The Subterranean Arsenic Vault of Giant Mine. On the shore of Great Slave Lake near Yellowknife, decades of gold processing at Giant Mine between 1948 and 2004 generated a hazardous industrial byproduct, arsenic trioxide dust. Because gold was locked inside arsenopyrite ore, high-temperature roasting was required to liberate the precious metal, producing gaseous arsenic that was captured and collected. To safely contain the toxic material, mine operators pumped 237,000 tons of highly soluble arsenic trioxide dust into 14 underground stopes and chamber voids carved into surrounding permafrost bedrock. Environmental scientists using core sampling and deep thermal monitoring arrays found that as climate warming thaws surrounding rock, groundwater could dissolve trapped arsenic. To prevent contamination of Great Slave Lake, a perpetual care program was established, utilizing specialized underground freeze plants that circulate chilled brine through subsurface pipes to keep rock and toxic dust permanently frozen in place. What happens when these engineered subterranean boundaries encounter unpredictable changes in surface conditions? Item 7. The thaw slumps of Tuktoyaktuk. Along the Arctic coastline of the Northwest Territories at Tuktoyaktuk, permafrost degradation is actively restructuring the land. Ground radar and thermistor monitoring arrays operated by Natural Resources Canada reveal that underlying coastal terrain consists of massive ice wedges and retrogressive thaw slumps, where ice content exceeds 80% of total ground volume. As summer sea ice retreats and air temperatures rise, wave action directly attacks unshielded ice-rich bluffs. Entire sections of coastline are collapsing into the Beaufort Sea at rates exceeding 2 meters per year, threatening municipal infrastructure, historical structures, and residential areas. The cost of shoreline stabilization and phased community relocation is estimated by engineering studies to exceed $100 million, demonstrating how subtle thermal changes in subsurface ice can force the physical relocation of entire Arctic settlements. Item 6. The abandoned cobalt shafts beneath town infrastructure. In 1903, construction of the Temiskaming and Northern Ontario Railway exposed rich native silver veins near Cobalt, Ontario. Over the next several decades, miners excavated thousands of shafts, adits, and underground stopes directly beneath the town site, extracting over 460 million ounces of silver. When mining operations ceased in the mid-20th century, detailed underground mine plans were archived, but many shallow stopes remained unsupported, just meters below surface streets and homes. In recent decades, mine hazards monitoring programs conducted by the Ontario Geological Survey have identified severe structural subsidence and sinkhole risks where shallow underground voids are collapsing. Remediation crews have spent millions of dollars backfilling historic shafts with concrete, installing heavy steel caps and monitoring ground displacement, proving that long-forgotten underground extraction continues to dictate surface safety and municipal planning. Item 5. The submerged foundations of the lost villages. On July 1, 1958, engineers detonated a cofferdam along the St. Lawrence River, flooding 38,000 hectares of land to construct the St. Lawrence Seaway and Saunders Power Dam. The inundation drowned 9 historic communities, including Altsville, Dickinson's Landing, and Farron's Point, forcing the relocation of roughly 6,500 residents. Today, under calm water conditions, side-scan sonar surveys and hydrographic mapping by the Canadian Hydrographic Service reveal complete street layouts, sidewalk grids, foundation pads, and submerged canal locks of drowned villages resting beneath 6 to 12 meters of water. What appears on surface navigation charts as open water along Highway 2 is actually a submerged cultural landscape where underwater infrastructure dictates modern commercial shipping channels and recreational boat anchorage. Item 4. The structural stress of the Cascadia subduction zone. Off the western coast of Vancouver Island, the Juan de Fuca plate is subducting beneath the North American plate at roughly 40 millimeters per year. For centuries, European settlers assumed the coastal region was tectonically quiet, as no major megathrust earthquake had occurred since regional historical record-keeping began. It was not until the late 20th century that researchers analyzing drowned coastal cedar forests along the Pacific Northwest, combined with tsunami records documented in Japanese historical archives, confirmed that a magnitude 9.0 megathrust earthquake occurred on January 26, 1700. Indigenous oral histories across Vancouver Island had preserved accounts of this catastrophic coastal subsidence for generations. Today, continuous GPS monitoring arrays operated by the Canadian Geodetic Survey track active crustal deformation, showing that strain is accumulating along the locked fault zone. Regional building codes, tsunami escape routes, and critical bridge engineering across British Columbia are now designed directly around the certainty of a future megathrust rupture. What happens when these ancient geological thresholds, historical engineering choices, and invisible subterranean structures are brought together under a single analytical lens? Item 3. The unplowed boundary of the Suffield Reserve. Inside census divisions of southeastern Alberta lies a territory spanning 2,690 square kilometers that has remained almost entirely untouched by modern agricultural plows, the Suffield National Wildlife Area. Created within the larger Suffield Military Range, this expanse of native mixed-grass prairie was closed to homesteading and public entry in 1941. Because European settlement across Western Canada systematically broke prairie sod for wheat farming, less than 15% of original native shortgrass prairie survives across interior plains. At Suffield, the absence of cultivation preserved thousands of pre-contact archaeological features, including bison kill sites, stone medicine wheels, and ancient trail networks mapped by researchers from the Provincial Museum of Alberta. The military boundary inadvertently created a massive ecological and historical sanctuary, preserving an unplowed prairie landscape that was elsewhere erased by standard cadastral subdivision. Item 2. The ice patch hunters of the southern Yukon. High above timberline in the southern Yukon, melting ice patches along alpine ridges are releasing thousands of years of preserved organic technology. Beginning in 1997, wildlife biologists inspecting caribou dung along snowbanks discovered ancient hunting weapons, including atlatl dart shafts, sinew bindings, foreshafts, and feathered arrows. Radiocarbon dating conducted by the Yukon Paleontology Program revealed that the oldest recovered darts date back over 9,000 years, providing a continuous record of subarctic hunting technology used by ancestral First Nations. Unlike glaciers, which grind underlying material through movement, these stationary ice patches preserved delicate wooden and biological artifacts intact. As summer temperatures rise, these ancient organic tools melt out of the ice, disintegrating within seasons if not recovered immediately by joint field teams operating with affected First Nations, demonstrating how subarctic ice holds a fragile, rapidly disappearing archive of human land use. Item 1. The impact ring of the Manicouagan Reservoir. Visible from Earth orbit as a vast, circular ring of water, the Manicouagan Reservoir in central Quebec defines the largest visible impact structure in North America. Known as the Eye of Quebec, the ring-shaped lake fills an annular moat roughly 100 kilometers in diameter, surrounding a central elevated island of metamorphic rock known as Mont Raoul Blanchard. Geologists using argon-argon isotopic dating determined that the crater was formed 214 million years ago during the Triassic period, when an asteroid roughly 5 kilometers wide struck the Canadian Shield at hypervelocity. The impact released energy equivalent to millions of nuclear detonations, melting hundreds of cubic kilometers of target rock and generating a central peak that rebounded upward like liquid. In 1970, Hydro-Quebec impounded the Manicouagan and Mouchelagon rivers behind the Daniel Johnson Dam, flooding the outer impact trench and transforming an ancient cosmic scar into a massive hydroelectric storage reservoir. What kept these hidden structures unrecognized for so long was not their depth or remoteness, but the assumption that a flat surface line implies an equally simple geology beneath it. Many of these subterranean boundaries, buried drainage channels, and melting ice archives remain actively contested, under-monitored, or undergoing rapid physical transformation right now. The official map sheets appear neat, complete, and fully surveyed, but the physical ground beneath them is continuously moving, thawing, and revealing what lies buried. Which landscape anomaly in your own province or territory has always struck you as strange, or which item on this list surprised you most? Let us know in the comments below, and consider subscribing for more deep geographical investigation.